Good morning. My name is Heather Wells. This morning we're going to be talking about weld discontinuities. Some people may think of these as defects, the parts of a weld that or in the base metal that will make it fail whenever it's put under any type of stress. So the things we think about are kind of the undesirable looking welds, but it goes deeper than that. So we're going to talk about those different discontinuities. First, I want to start out and show you, this is a really great visual representation. Lincoln Electric does a good job of putting these handouts and posters out for people to use. I really like them because not only do they show a picture so you can see what you're looking at or looking for, it also tells you what the possible causes are and what you can do to fix the weld so you don't get that discontinuity in the future. So first we're going to talk about the things that contribute to undesirable welds. So it all goes back to our power source, so the welder. We need to start with good settings. Things we can set for stick welding, we would control our amperage. For some of our wire fed processes, we would set things like our voltage and our wire feed speed. We'll talk about just mainly stick welding today because it's the main process that most welders use, and it's also kind of the easiest to explain some of the different human errors that go into effect. So when we're looking at our machine, we want to make sure that we have the correct amperage set on our machine. There are some really good resources for this if you're trying to look for a baseline of what to run. ESAB makes a really great application for your phone. So does Miller. It's called Miller Weld Settings. These are really great to kind of have a jumping off point for what you're going to set your machine at. So things you would put in, what type of metal are you welding on, and what size and type of electrode are you using, or the stick for this shielded metal arc welding or stick welding. So you take a peek at that and it would give you a range, and usually we want to start somewhere in the middle of that range. For a less experienced welder, we're probably going to be on the lower end of that range because a hotter weld is tougher to control. For a more experienced welder, we might go on the higher end of the settings because we get that really great penetration and we're able to control the puddle through those years of experience and knowledge. So we really want to start at that point. And we want to do some test runs. Always warm up before you weld. See how the machine's running. We don't want to take a nice weld joint and put a bead in it and find out we're on the wrong settings or our leads are mixed up. So really make sure that things are good to go with that. Always warm up. Make sure you're comfortable. Make sure you have everything you need in your booth to clean your weld and to run the weld in between. Some tools we want to have with us, files, and I'll get to why those are important in a second. So our files, our chipping hammers, and our brushes. Stainless steel brushes are really great for helping clean our weld in base metal. Grinders too, we don't like to grind, but if we have to, we can grind. Some procedures do allow us to do that, especially if we get one of these discontinuities. We have to make sure we take that out instead of just welding over it. So once we've got our machine and we're all set up and good to go, we want to make sure we're paying attention to what I like to call the human errors. So these are all of the things that are controlled by the welder through his or her movements and positioning. So some of those start with things like travel speed. So as we travel along a weld, say I'm doing a vertical weld here, I want to make sure I have a nice consistent travel speed to where I'm depositing the filler metal at a nice even rate. This is typically measured in inches per minute and it would fall into our procedure. Most welders don't time themselves and see how long it takes them. They do it by our experience and just kind of trial and error. So once we've got our travel speed good to go, we'll see a nice even bead. If we travel too quickly, especially on a piece of base metal, what will end up happening is we'll see kind of a disconnected weld, or we'll see a weld that just kind of sits on top of that metal. If we have a weld bead that we're running too slow, We have a really convex weld, and it's a lot of filler metal deposited. When we do this, we get a lot of extra heat input, and that's the same as taking that amperage on your machine and cranking it right up. So it's not only the machine settings that you need to worry about for heat input, but also what the welder's doing. That travel speed is really important. Other things that can affect our heat input are going to be welding a lot of subsequent beads. So if we don't give that metal a little bit of time to cool in between and we just keep laying bead after bead, you'll see that become cherry red. That's no good. So typically we try to keep our base metal at 500 degrees. This is for structural, just base metal, regular steel. We try to keep it 500 degrees or less. If we get over that 500 degrees, the things that happen are your heat affected zone start to spread out beyond your base metal. So the heat affected zone, if I had a weld here, is going to be the area in the base metal outside of the weld that's actually affected by the heat. So this can cause some structural changes to the base metal. So not only would your weld have been run too hot, but then that base metal could potentially be weakened. So not only could your weld fail, but also that base metal could fail as well. Some of the other human errors we have are angles. So we really want to make sure that we're using proper angles when we're welding, especially stick welding. It's very apparent. So if we have a piece of metal here, say I'm doing a vertical bead on this piece of metal, I have two different angles. I have one, if I start here, say this is 90 both ways, my travel angle for vertical is going to be this way. So we always want to make sure we're maintaining 5 to 10 degrees on that vertical travel angle. But then I also have a work angle. That's where in the weld joint am I pointing that electrode. That work angle is equally important. So you can see you have an x-axis and y-axis that you're creating angles over. So we really want to pay attention to those things. Another human error is your positioning. So where are you pointing that filler metal? So not just the angle at which you're pointing it, but where are you placing it in that weld or in that groove rather, or if you're in a T-joint, where am I placing that? Am I placing it up more on this vertical plate or more down on that horizontal plate? That's really important. And then lastly, we have arc length. Arc length is really important because it affects our weld. This is sort of counterintuitive, but people typically think that if I pull my arc away from my base metal, that I'm going to have a colder arc or lower amperage. Contrarily, that actually increases your resistance and in turn increases the amperage for that weld. So we really want to make sure we're maintaining a correct arc length. So the arc length, the rule of thumb, and once again, some different positions, different things call for some exceptions to this, of course. But we typically go off of the base end, the bare end of the metal, and we use that. So if I'm using an 1/8" 7018 electrode, I would be about 1/8 of an inch away with that electrode from the base metal. So that would be my arc length. And you can see it, it's that really bright glowing part at the end of your electrode. It's where that electricity is crossing. So those are all of your human error type things that contribute to these different types of discontinuities. So we'll start out here on porosity. I like to call this the Swiss cheese looking weld. So porosity can be caused by a few different things. Primarily in stick welding, it can mean a lack of flux on our electrode, whether it's chipped off or you're reusing an electrode and that bare end isn't covered any longer. We can end up getting some of that porosity because we're getting contaminants from the outside air pulled into our weld. Some other causes for that, we talked about that arc length. So say I'm using an 1/8" electrode. If I pull too far away, I can end up getting porosity in that weld. Some other things, dirty base metal. So as welders, we like to weld. We don't like to grind, right? However, anytime we don't take the time to clean our base metal, it makes our job a lot harder. So what we need to do is take that extra step before we lay down any welds and make sure our base metal is nice and clean and free of contaminants. Some of these things are mill scale. We can have oils left on from the cutting processes. So whether it's lubricant from a saw or something along those lines, we want to make sure that our metal's free and clear of all of that. Just make sure we take off that mill scale. That mill scale can also cause those discontinuities and become part of our weld, which is not what we want. So those are all the things that can contribute to porosity. Porosity is very undesirable, and it would not help you pass a visual test in welding. Our next discontinuity is undercut. Undercut can be caused by a few different things, mostly angle. If we are not pointing our electrode where it needs to be pointed and we're melting some of that base metal away but not filling it back in with our filler metal, we get kind of a void. And I like to say it's right at the edge of your weld. It sort of looks like a dog took a bite out of your base metal right next to your weld. That's what's called undercut. Some other things that can contribute to this are going to be your travel speed. So if we're traveling too fast, we might be melting away that base metal, but once again, we're not pausing long enough for that filler metal to fill that void back in. And then of course, we see this a lot on what we call the cap or the reinforcement, that top set of beads, where people have let their weld get too hot, and then we get that undercut. So it's essentially the same as taking and cranking up that amperage on your machine and trying to control that puddle. So you have to move quicker, and as a result, you don't fill in those voids, and we get that undercut. So it'll look like dark spots. A really great way to see this is to take a flashlight and shine it right along the edge of a plate, and you'll see those shadows where there's undercut just pop right out. AWS says you can't be, the American Welding Society standards say you can't be any deeper than a 32nd of an inch for that undercut. 30 seconds sounds like not very much, but when you look at it, a 32nd is pretty deep. So we want to make sure that we're not getting any undercut. I don't like to see any. I really strive when I'm welding to not get any of that undercut. I really want the prettiest bead possible, and cover, especially that nice cover pass. Next we have what's called excessive reinforcement. So this is on the top of our weld, our last set of beads that we lay down. We want to make sure that they're not any higher than 1/8 of an inch above the base metal. So that's the top of this reinforcement down to the base metal needs to be less than 1/8 of an inch. And the reason for that is most people would think, well, more is better, right? If I put more weld down, it's going to hold better, it's going to be stronger. Well, our engineers will tell us that the more weld metal I lay down on the top, the bigger an angle I create right here. Anytime we have a large angle, nearing on 90 degrees between this base metal and this weld metal right here, I create a stress point. So that's a stress point that can actually end up breaking and causing cracking right here in the edge of that weld metal. Most companies are between flush and 1/8 of an inch for your reinforcement. Some companies don't necessarily care, or some procedures don't call for any maximum reinforcement because they'll actually machine that down afterwards, so it doesn't have the same effect. But where we're leaving something as welded, we want to make sure that we're not putting too much of that reinforcement there. And we can get that excessive reinforcement through a couple things. One, if we haven't planned our trip out to the top well enough to where we have to put too much weld on the top, right, to fill it in. Another thing is if we're traveling too slow, once again, we're getting a very convex bead, and it's going to look kind of piled up on top rather than blended between our other beads and our base metal. So we really want to aim for that pretty reinforcement on the top. We want it to be visually aesthetic. On the opposite side of the spectrum, we have what's called underfill. So underfill is where I'm filling in a groove weld here, and I haven't quite come to the top. I haven't quite come up to the level of that base metal. So by and large, your expectations for a weld are going to be from flush, so that's flush with this base metal across at least without any concavity, up to 1/8 of an inch is maximum reinforcement. So those are our goals for when we're filling in a groove weld, say. Now things kind of change when we get to our T-joints. This here is a T-joint here. What I've shown in this one, this discontinuity, is called overlap or cold lap. The reason it's called cold lap, you might guess, is that a lot of it is caused when we're running our amperage too low. So we get what's that kind of cold bead that doesn't really blend into our base metal. A desirable weld would kind of look like this. So where you can't really tell where I'm blending in. It kind of just blends right into the base metal and goes back like that. With this one, you can see this cold lap. I kind of have this void underneath the bottom edge of my bead, and it kind of looks like I put cold frosting on it. It kind of just drooped down. So we want to make sure that we're really tying in. So whether we're tying into base metal, where we have that smooth transition between weld bead and base metal, or into another weld. We really want to make sure that everything is tied together. Tying our beads together is going to give us that strength that's necessary in any sort of pipe or structural welding processes. So really make sure we're paying attention to that. Some other things that can cause that are going to be your angles. So remember, we talked about those travel angles and work angles. So this, if I had my work angle and I was aiming more on that vertical plate, and then it kind of drooped down because gravity, we might end up with that little bit of cold lap or overlap on the bottom edge of that. So think of it as sort of looking like that droopy frosting. Next, arc strikes. Arc strikes are completely undesirable in welding. They can actually affect your base metal and cause that to become weaker where you've struck the arc against it. So an arc strike is defined as any sort of strike outside of our groove or our weld joint. So this is left over after we're done welding. We all aim for that nice pretty weld, and then nothing ruins it more than having that arc strike in the base metal right outside of there. So that's an automatic non-visual pass. So we really concentrate, especially on our restarts, making sure that we're starting that arc up inside our weld joint. So we can completely tie that back in and cover over that with our weld metal. Really, really important. Next we have slag inclusions. Slag inclusions can be caused by a couple different things. Mostly it's improper welding technique. So especially in a groove weld, if I don't have that work angle quite right, I can end up with slag in there where I can't get that back out with my chipping hammer or a file or a brush. And then a simpler reason to get those is actually from those slag inclusions is actually from people just failing to clean in between welds. Everyone likes to weld, but we do have to take that extra step, cleaning before we weld, cleaning interpass, so interpass weld cleaning, whether we're using mechanical means, our hand brushes, our chipping hammers, our files, or if we're using a wire wheel. So those are some different things that we use to clean. There are also needle descalers that we can use to clean those that usually run off air. But we want to make sure that we're really cleaning and we're not creating any little pockets in our groove weld where we can trap that slag. We don't want to trap it. And once again, that goes back to proper bead placement and those angles, really making sure that we're tying everything together. So in closure, going over what to look for, we really want to identify these discontinuities and then practice how to keep them from happening in the future. This is really, really important to nice sound welds, and also really important to passing visual tests. As we become welders for a career, we may have to take several tests, whether it's for a company or it's for the American Welding Society. These weld tests are going to look for these discontinuities. Some of them may not be apparent from a visual test. So like a slag inclusion in here, we're not going to see that with a visual test on that. Things like underfill, excessive reinforcement, you'll absolutely see those. Arc strikes, that's going to stick out like a sore thumb. Undercut, you may see it on the top, but you may not see it if it's inside the weld. And then your porosity will absolutely show up if it's on the top bead. However, if you get porosity underneath in your initial beads, it is like cream. It always sort of rises to the top. So don't try to think that you can cover up your porosity by going over it. And then what's not seen through a visual weld test is going to be seen through your destructive bend test. So those discontinuities really come to light when we start putting some stress on that weld metal. So we all aim for that nice pretty bead. Nobody wants to paint over or grind our welds. We really want to be proud of the finished product that we put out there. So good luck, guys, and aim for perfection.